Yeah, no, it's recorded.
Yes. Okay. I have uploaded the slides to the Piazza. So if you like to take notes, you can download from Piazza. Welcome everyone. Well, back to our GPU programming class. This is the second lecture, the third class. Today we are going to talk about finally the CUDA programming language. We will cover some basics of how to write your CUDA program, and we'll talk about the execution model behind it and how it ties to the GPU architecture. Then we will talk about the profiling tools for the NVIDIA, which will help you benchmark or optimize your GPUs. Oh, if you have questions, you can type in the chat. I will stop and look at that, or Chunani will remind me. So why do we need to learn CUDA? Why is so important? It is the language that started the GPU excitement. GPU here is the general purpose GPU. So we use GPU to do we used to do it for graphics processing, but now we use it with more purpose. In theory, CUDA only runs on NVIDIA GPUs, but there are lots of research paper and scientific paper and research work that tries to translate the intermediate language that CUDA's compiler compile and translate the intermediate language into binaries that you can run it on other target such as NVIDIA GPU. So as you can see, as a high performance programming programming framework, the NVIDIA provides you with nice libraries, which is like high-level API that allows you to use the super optimized kernel instead of implementing by yourself, spend time trying to figure out how to speed up your kernel. You can directly use the kernel provided through the library. So for the learning curve, since it is similar to C and C++, so if anyone who has experience with C or C++ should have no problem finding out how to use CUDA. So the purpose of CUDA is give some abstraction and help you make your code. So it gives some abstraction and make your code run on the GPU in a run on the parallel platform. Mainly, I mean the GPU, the NVIDIA GPU. CUDA is a standard NCC-like language. So also the CUDA API, the application programming interface, can let you manage the device, the memory, and do the synchronization and etc. So let's talk about the APIs. There are two levels of APIs. The first one is driver API, which is a lower level API. The lower level So the other is the runtime API, which run on top of the driver API. We will use the runtime API. So let's take a look at how does CUDA look like. So on the left, you will see a C code, which is the for loop. On the right side, you see the CUDA code. So in the CUDA code, you will see the blocks and grids. These are the concepts of CUDA. So please keep in mind of that. We will mention that later, give more details. So what is a grid and what is block? And there is also a concept of kernel. So kernel is a single stream of instructions that will operate on a large number of data in parallel. So executed by each thread. So when we have thread, so the block will be executed, the whole kernel will be executed by a large number of threads. And the threads are inside a block, which is part of a grid. We will see the concept in next slides, which will give you a better understanding. So basically what this code do is on the left side, you can see the index. It's like two indexes, I from 0 to max I, j index j from I to max j. So what you will do is do something inside the kernel using the index. So you can imagine it's like accessing a matrix. One dimension is 0 to max I, the other dimension is j, is 0 to max j. So the CUDA kernel can do the same thing, but use the block ID, the blocks IDX and thread IDX, as you see here. So those parameters are associated with the kernel you launch. So you can split your problem and send your kernel to compute by each thread. Now, the CUDA has this concept of a host and a device. The host is the CPU, so you will run some of your code on the CPU. So it will execute your main function and launch and will do some CPU related jobs. The device is the GPU, so it will responsible for executing your kernel. So when you code your applications, you have the concept of the host and the device. So you need to write two parts of code. In order for you to run things on a CUDA device, you have to write a device code, which is what we call the kernel. And then we have to other things from the CPU, like allocate memory on the GPU and transfer the data from CPU to GPU, then transfer the result back to CPU. So this shows the flow of the CUDA programming. So before you copy the data from CPU to GPU, there's one thing you have to do is to allocate the space on the GPU. CUDA provided this API, CUDA malloc, to do this memory allocation. So you pass the pointer, and this pointer is the beginning address of the memory range you want to allocate on the GPU, and also pass the size, the memory size. Then this API will do the allocation and return the address to the pointer. So after that, you have the pointer of the allocated memory on the GPU. Your next step is to do the mem copy. You have the concept of destination and the source. So it's normal that you first have your data somewhere located in the CPU. In the normal cases, you have the data located in your CPU, and then you would like to transfer to the other places where is the destination. So you pass the CUDA man copy function the references to those two data. One is the data on the source. The other is the memory address on the destination. Then the size of the data. So if the source is the host site, the destination is the GPU. So you will see the fourth flag is the CUDA man copy kind, which is if you transfer from host to device, the flag will be CUDA man copy host to device. If you transfer the result from GPU to CPU, it will be CUDA man copy device to host. So the next step is to invoke the kernel. Invoking kernels, this is the you have to be aware of several CUDA abstractions and their hardware counterpart. I mean, like the grid, the block, the kernel. Yeah. The kernel is actually executed by the grid, and the grid may have multiple blocks of execution, which can be indexed in 1 dimension, 2 dimension, or 3 dimension. In this picture, we have 2 dimension blocks, and each blocks may have multiple threads. All the blocks, so look at here, we have 15 threads here. So the number of threads in a block is 15, but 15 is not a good number for the number of threads in a block. We will see why in the next few slides. So the other thing I need to mention is the the number of threads in the block is the same if the block are all in the same grid. Let me rephrase that. So all the blocks in the same grid have the same number of threads. So there are 6 blocks, and each block has each block has 15 threads. So let's think about an application. Assume we would like to add 2 vectors. So we add the element in each vector, element by element, and put the result of each addition in another vector, C. So if you would like to execute it in a parallel manner, suppose you have a CPU with multiple cores, what each core will doing what kind of operation. So this is a question that does anyone have idea? So what I mean is, so you just need to add 2 vectors, but using multiple cores. So what does each core will do? So I think the sensible way to think is that we can do, so in each core, you can do just one addition. If that core is the CPU core, that may not be a good choice because the CPU core are able to do more complex thing. But for if that's a GPU core, GPU core are much simpler, and there are many of cores in the device. So it will be a good strategy to split the job among different cores instead of having one core doing the full loop to do all the addition. So what if we want to add a 2D array? So the same thing here is we add the element by element in the 2D, in the 2 arrays. So if we, that's where the multi-dimensional block and multi-dimensional grid may come in handy. So if we map our matrix to the block, like the matrix, we can use the thread, like we map the matrix to the block, we can use the thread 00 to thread 42, those threads to calculate the addition for each element. How do we access the thread? So we will use the thread index. I will show how to do that later. Still, let's talk about the multiple blocks are combined to form a grid, as we talked before. All the blocks in the same grid contain the same number of threads. The threads of a block can be indexed in 1 or 2 or 3 dimensions. So those parameters are very useful. I hope you will understand them and you will be using them in the lab. So when we talk about the grid size, which means how many blocks in the grid, so if that is so there are multiple dimensions for a grid, so that's the gradient X, gradient Y, gradient Z. And to index each block inside the grid, we have the block index. And for the threads, so when we talk about the block size, which means the number of threads in the block, so go back to the picture, we will see, so the block dimension X is 5, the block dimension Y is 3. So how many threads in a block is 15, we can see, but if you say that based on the dimension, that will be the multiplication of the 2 dimensions. So the same thing for the grid, the gradient X is 3, gradient Y is 2. So we can calculate the number of blocks. And inside each block, we have the thread index XYZ to index each thread inside the block. So, so one important thing is how do we figure out what number of blocks per grid and the threads per block we should choose. We need to first consider your problem. So, and also consider the hardware, the device hardware specifications, like the number of CUDA cores and how many blocks I can run at a time in order to, so these conditions will help you decide the number of blocks per grid and the threads per block. So one thing I have to point out is you have a choice to use this theme3 data type, which is just a C struct with 3 variables X, Y, Z to indicate the dimension of your block or grid. So here we create a variable called the block, which means the block dimension, the block size, which it is the number of threads in the block is 32. And we create another variable grid, which is the number of blocks by calculating how many blocks we needed. So you know how many threads are, if you know how many threads in a block, and you know how many threads you would like to spawn. So in this case, we the number of the number of threads we would like to spawn is the number of elements. So it's very trivial. So if you would like to add 1,000 vector, I mean the length of the vector is 1,000. You can spawn 1,000 threads. That may not be a good number, but I just used it for example. So next, we will see how to call the kernel after you calculate the grid size and the block size. So the kernel name comes first, and there are 3 less than brackets. Inside these brackets, you put your grid size and block size you defined before. After that is just the argument list. So it's the same as you do when you call a regular function, but here you have to add this 3 less than brackets. One more thing is how many threads do I spawn? So this is also a question. Does anyone know the answer? So it's similar like this in the picture. How many threads do I spawn?
Yeah, there is answer, Yui, on the chat.
There is answer on the chat?
Okay. Yeah.
Yes, correct. It's a grid size multiplied by the block size. Yeah. Thank you. So next is also very important. So we have all the threads. They are grouped into blocks. They have their local index in each block. But how do we tell each thread stand for a unique element? Which also means how do we get the unique global index of each thread? Let's see this example. So we have this kernel configuration is 1496 and 256. The first one is the number of blocks we have. So we have 1496 blocks. So their index number is from 0 to 1495. In each block, the number of threads are the 256. So if we look at this number, it's the fourth thread in the block 2. How do we calculate the global index? So it's not difficult. So look at you can just count. So if you add those first blocks, that will be 512. So then plus 1, 2, 3, 4. So that will be 1, 2. I think the answer is plus 3 is 1, 2. Oh, it's the index. So it starts from 0. So that will be 215, 212, 212 plus 3, that will be it's 512 plus 3, that will be 515. So this calculation is important because you need to use the global index to access the matrix, access the data in the kernel. You will use this in tomorrow's lab. When we talk about writing kernels, so there are two qualifiers. One is global, one is device. The global means this is the kernel, and that will be executed on the device and callable from the host. This is the only kernel. This is the only device function you can call from the host. And if a function has the device qualifier, which means this device can only called from device, so which means it can call from another device function or a global kernel. There are some restrictions. Those kernels are used the device memory, which makes sense. We run our application on the GPU side, and there's no support for variable number of parameters, which means for the kernel function, we only have fixed number of arguments. It has here is an example. It's an example program of a simple CUDA program. So I would like to point out this is the host program. So the flow is your used CUDA malloc to allocate the memory on the GPU. You copy data from CPU to GPU. Once you figure out the number of threads in a block and the number of blocks in a grid, you can call the kernel. The kernel is called the matrix multi kernel. From the name, you can tell it is doing matrix multiplication. Once you call the kernel, the CUDA copy, the last CUDA copy, which is from device to host, has the feature that it will wait until the previous API finished. So the previous task finished. The task on the GPU is the kernel call. So once the kernel call finished, the CUDA copy will do its job, is to copy the data from the device C and back to the C in the CPU. So this is the kernel. So tomorrow we will do a relative easier example, which will be a vector add. So if you are interested in the matrix multiplication kernel, you can look at the code. It's not very difficult, but I won't talk about in the lecture. If you have questions, You can ask after the lecture or post your question on the Piazza. So this program just give you a feel of what is a whole CUDA, what is a whole CUDA program. So you have the host code, which do the flow of the CUDA program, and you have to write your kernel, which is this one. So the next step is once you have your CUDA program, you need to compile it, use the NVIDIA CUDA compiler called NVCC. It's very easy. It's the same as you do GCC. Then you can run your, so when it generates the executable, you can run your executable. So in this host function, in the main function, it do the two things. One is do the matrix multiplication using CPU, and also do it using GPU. That's why you get 2 times here. Until now, we have covered all the software side of CUDA. We went through the basics of the software side of the thing CUDA provide. Now we will look at the hardware side. So the reason we need to understand how the GPU architecture in the device, because we need to use the software side, the concept, to leverage the hardware. Yeah, that's the question I answered. Why do we need to learn the hardware details about the code execution and how your code is get executed? So as I said before, we use GPU to get a better performance. So how to do that? It's the kernel configuration, which you as the user is responsible to give this configuration, and that will depend. So the number you choose will impact the performance of your application. We will go over the architecture while explaining how a kernel executes on the GPU. We will focus on the Kepler architecture. So the GPU we will use in the lab is a Kepler K20. So this is I think this is the Kepler K40 chip. On this chip, you can see those blocks. So this is called a streaming multiprocessor. There are 15 streaming multiprocessor. So inside each streaming multiprocessor, you will see this small grid, which stands for CUDA, which stands for core. How many CUDA cores inside? I think, if I'm not mistaken, there's 192 cores in each streaming multiprocessor. So how many cores do we have on the on the Kepler on this chip. That will be 192 multiplied by 15. It's over 2,000 cores. So in the best scenario, we'll see later what is inside the streaming multiprocessor. And here, if you look at the blue part, it's a L2 cache shared among all the streaming multiprocessors. Inside the streaming multiprocessor, there is another blue is L1 cache shared by all the execution, all the warps, all the execution inside this streamer multiprocessor. This talks about what is inside the multiprocessor. As I said, the CUDA cores, the shared memory, the register file, the low store units, and the special function units and warp scheduler. We will talk about what is a warp, which is a very important concept. Yeah, on the right side is the specification of the Kepler K40. So we have total number of cores, 2880 cores, which is a large number of cores. So this is called a massively parallel processor. So how a kernel is launched on the GPU? As we mentioned that we group the threads into thread blocks. This is mimic the way we group the cores into the streaming multiprocessor. So that indicates how we use the software concept to leverage the real hardware structure. So the CUDA execution model issued these thread blocks to the multiprocessors. Once that is issued, we call it a block. It's issued to a streaming multiprocessor. It stay on that. It won't migrate to other SMs. So multiple thread blocks can concurrently reside on SMs as long as there is enough resources. The resource, when I talk about resources, that means the register file and the shared memory. Yeah, as I said, the kernel is chunked into thread blocks, and the thread blocks are sent to the streaming multiprocessor for execution. So the threads that we now only talk about the threads inside each blocks. They will be executed simultaneously, but not exactly. Yeah, as I said, multiple blocks can be assigned to the same SM, but that doesn't mean they can be executing simultaneously. It will depend on the resource on the SM. This is the logical and physical view. So I think this picture show what is the thread and that corresponds to the core on the hardware side, then the threads are grouped into blocks which maps to the streaming multiprocessor. The streaming multiprocessor will execute multiple blocks. We can see at the same time, but all the threads in all the blocks may not simultaneously running the same instructions. Then the blocks are grouped into the grid. Actually, that's how the device is organized. I think I will bring the concept of the warps first. So in this case, the blocks is not the smallest unit of computation. The warps is all the threads in a warp execute the same instruction at the same time. So that means all the threads in the warp run simultaneously. So the blocks is chunked into groups of 32 threads. So that means there are 32 threads in a warp. And those 32 threads will execute the same instruction. Each SM will partition the blocks into warps and schedule them for execution. So yeah, it is possible that threads on the same warp could have different behavior. Now let's look back to how the kernel. So in this picture, the kernel composed of 4 blocks. In each block, we have the thread. There are 256 threads in the block. So the GPU will launch the blocks into the streaming multiprocessor. So the logic behind the scheduling is first, they will try to, if one if one SM is busy, it will try to find the next one to check if that is free. It will launch the block into that SM. So how many blocks do you need to occupy all the streaming multiprocessor? That is a question. So the answer is the number of streaming multiprocessors. So in that case, if each SM only handle 1 block, so that will be 15 blocks. So that gives you a hint of how many blocks do you need to choose. Also, the size of the block is very important. So before the block is launched to that streaming multiprocessor, it has to make sure that the SM have enough resources for this block. If you have a large block, we will see in the next slides. So if the block is too large, even one streaming multiprocessor couldn't have enough resources, the whole kernel will stall. On the other hand, you have small blocks, so you can allocate that, so you can launch that blocks to each streaming multiprocessor. So like if you have, here I said if you have 15 blocks, each streaming multiprocessor will have one. So when you have more, like the next one, if you have 16, so the first one will, the last one will be scheduled to the first stream multiprocessor. It will ask it if it has the resources. If it doesn't, which means the last block won't be executing until one of the streaming multiprocessor release the resource, which means that they finish their own block, then they can take the next block. That's why I say all the threads in the kernel doesn't run exactly at the same time, but they run like in they run in logically they run simultaneously. So let's go back to see what is a warp. So here the warp is 32 threads grouped into a warp, and then each thread, so as I said, the warp is the basic unit of execution. So the warp scheduler is responsible for schedule the warp inside a block. So you can see the block composed of the block comprised of here is 5 warps, and those warps will be scheduled to the cores to the streaming multiprocessor. Let's see. This is also very important. Like I said, the thread in the block is indexed by, it can be indexed, it is indexed using 3 dimensions. However, in the hardware point of view, the hardware only see these threads as 1 dimension. So that means if I have here 128 threads, so the first so the block of 128 threads will be partitioned into 4 warps. But for the programmer, they don't need to write anything, or they don't need to program anything related to the warp. It is totally handled by the hardware, but it's better you aware of this warp. The benefit of aware of this warp is if your block size is not a multiple of the warp size, you couldn't fully leverage the hardware. In this example, so you have a block with 80 threads. So you have to, so that block is split into 3 warps, but for the third warp, you don't have, you are not fully using the hardware. So if I, for instance, if you have a application only have 33 threads, so how many blocks do you need? No, I will rephrase. You only have one block in this application, and the block size is 33. So the 33 threads couldn't fit into one warp, so you have to so there will be two warps inside the block, but the second warp only have one thread working. The other 31 threads will do, they will be executing something, but in vain, because there's no data for them to run. So this width of warp can be aggregated, since I said I only have one block. But what if I have multiple blocks? That will increase the number of warps I waste. Here is the, let me see. Yeah. So let's take one block, for example. It is gets chunked into warps, and the warp scheduler, there are 4 warp schedulers in one SM here. So which means 4 warps can be issued at the same time and execute at the same time. Two independent structures per warp can be dispatched each cycle. This makes sense because you couldn't, if the instructions depend on each other, they could not be dispatched at the same time. They need to be dispatched in sequence. So in terms of the number of warps, there's another restriction. So this also indicates how many threads maximum you can have in one SM. I saw someone raise their hand.
Yeah, I just had a quick question. If if I try to issue one block with more than 4 warps, are all, let's say there are 6 warps of 32 threads each, will they all execute on the same SM because they're part of the same block, or will they be split across SMs, 4 on one SM and 2 on another SM?
If all these warps, so you are saying you just launch one block, is that right?
Yeah, one block, but with 6 warps. So more warps than one SM can handle. Will the 2 extra warps, for example, go to another SM, or will they be scheduled after?
No, they won't be sent to other SMs. Only, so all the block, I mean, one block can now be split into different streaming multiprocessors. So in that case, I think that means the one streaming multiprocessor couldn't run the block you configure.
They would have to sequential execute 4 maybe, and then 2 if it's 6 warps, right?
It depends on, so in that case, so here, so how many warps in your
My
block?
assumption, let's say 6.
So you can run at least, I mean, you can run at most 64 warps.
Okay, 64 warps. Oh, okay. So let's say the one block has more than 64 warps. Let's say I say one block has 96 threads, for example. So that's 128 warps. Would that block be split across SMs, or would the 128 warps be scheduled on the same SM, but one after the other?
So one thing I have to point out is that a block can only be dispatched to one streaming multiprocessor. So
okay.
If you have such a large block, so that won't be allowed you to set the number of threads. So like if you, in that case, you set your number of threads per block as 1496. So that is not allowed. So they set a limit. So if you code inside the CUDA, you couldn't set the number of threads per block over the 2048.
Okay, so this is a hard limit in both software and hardware. I can't have more than 2048 threads per block. Okay, okay, thank you.
No problem. Okay, so there are two concepts. Is the active block, which means the resources in this block has been allocated. So they are accept a certain block or a number of blocks. Just they are ready to run those threads, or they are running the threads. For the active warp, it can be a selected warp which is running, the eligible warp which is ready for the execution but not currently running, and the stall warp is waiting for the resources to, yeah, it's not ready for execution. As I said, the number of active warps will be limited by the physical resources. So even you dispatch 10 blocks into the SM, but the SMs, but only 5 of them can be running at the same time, because 5 of them occupy all the resources in the SMs. So some blocks, some warps, some threads are, I mean, the other 5 blocks are waiting for the resources. So SM is free to schedule another warp if some warp it can detect if some warp is idle, or it's waiting for the memory response. It can schedule another warp, because if it is waiting for memory response, memory communication. So the computation resources is available. So once the resource is available, the SM can schedule other warp. Still repeated, the other threads on the warp must execute the same instruction. So what happened, as I said, the 32 threads can behave differently. This is applied to the case there's the branch. For if you run code on the CPU, it has complex hardware to specifically handle the branch prediction all the branch stuff. But for the GPU, it's the way it handles branch is just stalling the threads in a warp. You can see that clearly. It causes this is called a warp diversion. So there are 32 threads, but when they are in the blue.
आज वो जंबला बना
अरे नहीं हर दिन नीट कॉल करेंगे
हाँ
Kanani, are you speaking in the lecture? I will continue.
Yeah, sorry, Yui, I just had an interruption. Sorry. Yeah.
Oh.
Yeah.
No, yeah. Here. When the thread is running instructions in the blue range, they all instruct the same. They all execute the same instruction. But when it came across the if condition, so some of the threads have to run the if clause, some of has to run the then clause. So all the threads has to run the same instruction. So first they will run the if clause. The one are not chosen. So one thread which is expected to run the then clause will still run the if clause. But the calculation result will be wiped. So only the threads run the if condition expected to run the if clause will get results. So after the if condition, after the if clause is executed, they have to run the then clause again. So the total number of execution cycles are the total amount of time is the addition of two clause. So that will be 5. But if there's no warp diversion, it will be only either 2 or 3 cycles. So you will see stalling threads is never a good thing. It will add the work. It will make some threads do some wasteful work. So before we are talking about the thread level parallelism. So here, just a mention, there's also availability for instruction level parallelism. This is very common in the CPU architecture. So here, the instruction A and B can run at the same time if the pipeline is structured to run them in the same pipeline. So the A and B can finish in one cycle. Now let's talk about the resources I mentioned. So here I'm going to talk about the register files for the Kepler K20. We have 64K byte KB register files. So each thread require their own number of registers to use to do the calculation. So in the picture, we can see if there are more threads. So each thread has fewer registers. But if we have fewer number of threads, each thread can have more registers. So when we launch a kernel, the number of registers for each thread is fixed. So that gives us an indication how many threads how many threads or how many warp we can dispatch to a certain SM. This is decided by how many register file do we have. So for example, if I have 64 threads, so each thread will have 1 KB registers. This is not 1K is looks like it's large, but if you have 1K is very large. So like the example I saw for the matrix multiplication, each thread only need 8 register. But if there's a large application, each thread may need 100 or even more registers. So we have to be aware of how many threads we can allocate it. We can group it into a block. Yeah. So if the resources required for each thread is large, and we group a large number of threads into a block, that will bring us to the case that there may not be enough resources to launch at least one block. Here, I think this is a very interesting configuration information we have to aware of in order to give the kernel launch configuration to better leverage the hardware. So the number of threads per warp is 32. This is never changed. This is all true around all true through all the CUDA device. As I said, the max number of warps is 64. This will give the limit of the maximum number of threads per SM. I think there's also a limitation for the number of blocks per SM. And I think so. As when I answered the question, I said the max number of threads per block is 2048, which is not true. It is 1024. So that's the difference between the software end and the hardware end. So this 1024 is required. It's a limitation on the software side. Since you can have more threads. So like you can have the maximum the 1024 threads and have the multiple blocks. But at the same time, this means the number of threads can all working on the maximum number of threads are actually running in each SM.
Just so I can understand, just a quick question. So, so I can have 1024 threads per block, and that's a software limit.
Yes.
And I can have at most 2048 threads per SM. So that means if I take the maximum number of blocks, sorry, maximum number of threads per block, 1024, I can have 2 blocks of size 1024 running on the same SM. Is that correct?
Yes.
Okay.
But,
thank you.
Yeah, I agree with you. But there's also other limitation of how many blocks you can launch for each SM.
So just to clarify one point, Yuhi, sorry.
Yeah, no problem.
Yeah, so just to clarify, you cannot control on which SM you launch block to. So it's all automatic done by the hardware scheduling. So even if you create like a, if you create multiple blocks, those will be independently issued to multiple SMs. So you cannot control the placement of which block you want to go to which SM. That is not determined by the programmer.
Yeah.
How would I size the blocks? How would I size the number of like threads per block then if I can't think about how they're going to run?
You'd have to decide on the software limitation, right? So its maximum threads per thread block is 1024, and you as a programmer need to only care about that. So this upper limit or this number of max threads per multiprocessor is more of a hardware thing that's going on. So that's 64 into 32, right?
Mm-hmm.
So the maximum threads per thread block is the number that you as a programmer need to care about.
Okay, and how do I choose if I have a problem that can be split across multiple blocks of smaller threads or smaller blocks with more threads? What makes me decide either?
Which one? Also, you need to decide between smaller blocks, and so the first thing is that you need to respect this hardware limit, right? So it needs to be maximum of 1024, and beyond that, so your block size needs to have this size, and that is independent of whether, like for example, you see this dim3 argument, right? So x, y, and z.
Yeah.
So multiplication of x, y, and z should not be more than 1024.
Okay.
Yeah, and then you need to calculate the number of the grid size accordingly, right? So you have to set the grid size accordingly so that this number is respected.
Okay.
Yeah. So then the grid will have multiple blocks, and then those blocks will be executed as the hardware says fit. But the important thing to know is that a single block cannot execute across multiple SMs. It will execute in one SM. The programmer does not have control over that.
Okay, but how do I choose the size per block? Something as simple as like, if it's a vector multiplication, and I'm trying to add 2 huge vectors of size size 1024. I can do that in one block because
Correct.
I have 1024 threads.
Yeah.
But I can also do it in 2 blocks of half 512, or I can keep breaking it down forever.
Yeah, so that's an optimization thing, right? So that's what I think is covered in the first lab. So you need to, so as a programmer, it's up to you need to understand the hardware to be able to map it efficiently, like how many threads. Yeah, so that's an optimization thing, and it's always comes up in like whenever you write a GPU program, you need to. They are basically tools that help you to get the correct number over time, and
Okay.
So that's part of optimization. Yeah.
Okay. Okay.
Yeah, but it's good to think about that. Yeah.
Okay. Thanks.
Yeah, I have something to comment. So in tomorrow's lab, you will have chance to change the number of blocks. Yeah, you change the number of threads in a block. So if the problem size is the same, you actually change the number of blocks. You can compare the difference of a small block, large number of blocks, or a large blocks, small number of blocks. What's the performance difference?
Correct.
Okay.
Yeah.
All right. Okay.
Yeah.
Thank you.
Yeah.
The point I mentioned in the lecture is just help you understand there are some limitations in the hardware and how those warps or how these blocks are launched into the hardware.
I understand.
Yeah. So the profiling tool is the third part of this lecture. So why do we use GPUs? We use GPU for performance. How do we measure the performance? So it's important for you to be able to measure how fast you can run your kernel. Could give you some capability of measuring how fast you can run. We will see some APIs. We use the CUDA invent API call to measure the execution time. This is part of the CUDA API. This is commonly used to measure the time. The stream, yeah, that's the default stream. So this is an example. You will see this in your in the tomorrow's lab in the program. You will use this structure, this flow to record the execution time. So first you create the event, then you start the event and stop it. Yeah. Here. Yeah. That the number. I mean, the name of the event in this example is called start and stop, but actually there are two events. So the events are sent to the stream. They will be executed in sequence. So here, once the two events get executed, it will give the time of that event happens. So the CUDA event synchronization. So there are three applications: CUDA event create, CUDA event record. So that's when the event happens, and the CUDA event synchronization is wait until the event get executed. So then, after the events get recorded, you can calculate the execution time, which is how long does the kernel runs. So that is a simple example of measuring execution time. We have more tools to measure the performance using different metrics. So I will briefly introduce the command line profiler we will use tomorrow. It can give you the computation time for each kernel, also the time for memory transformation, other matrix, and it will collect the other matrix. One thing is that it doesn't need to recompile. You can directly run the executable you generated. This is so if you would like to know more information, like the detailed information for each line, you have to compile it again, recompile it. This is an example of how do we use the mvprof. So mvprof is the command line profiler we will use in tomorrow's lab. So the simple way is just mvprof followed by the executable file. And you can add some flags to specify what you want. You can see what metrics it provides, and you can specify some metrics or the GPU GPU CUDA runtime calls. So here is the timeline of the CUDA runtime calls. One benefit of using this command line profiler is you can use this analysis metrics option to generate detailed performance data. And then upload it to your MVVP, which is the graphic profiling tool. So we will not use MVVP tomorrow, but if you are interested, you can download it. It will allow you to see some pretty graphs like this one, show you what could be the reason of the stall. So you can install the CUDA toolkit and use this MV and install the MVVP. So you can just open the previous generated detailed performance data in this MVVP to do more analysis. So that's almost all about today's lecture. There are a few takeaways. So basically today we covered the concepts of CUDA programming language, the flow of how to write a CUDA program. Writing a CUDA program is not that difficult, but how to get a good performance is what we need to think about it. It's not that straightforward. We also talk about the hardware side, hardware architecture like SM, and the configuration of the hardware configuration of the Kepler-20 we will use. Yeah. The last we talk about the mvprof, the profiling tool we will use tomorrow. So now we are ready for tomorrow's lab that will allow you to write to code your first CUDA program and profile it. That's all for today's lecture. Thank you. If you have any question, you can ask now.
I think there's a question in the chat. Oh, yeah, somebody answered it already. Yeah.
Do these profiling tools, I guess, help you determine the number of threads by, you mentioned how that if you have multiple registers per thread, it can increase the execution speed, such as like parallelizing some of the, I guess, instructions. So will these profiling tools help you determine these number of threads based on like how many registers you're going to need per thread?
It won't directly give you the number of the configuration you would like to have, but it will give you some hints.
Yeah, I mean the visual profiler, the NVPP visual profiler, that might actually give you more information sometimes. So it can tell you like whether you have too less threads or too much threads that is applying register pressure, etc.
Okay, and like and I guess the compiler automatically takes care of how many registers per thread how it gets divvied out.
Yeah, the compiler is responsible for doing the register allocation. And that is dependent on your kernel code, right? So how many registers are required for that block of code?
Okay, thank you.
I think you can stop the recording.